So today we are starting section 4.4. We're still talking about logarithms. Today is laws of logarithms. This section is going to be much more straightforward, I think, than the other ones. So the first two sections were just kind of, or rather the last two sections, getting used to logarithms. Well, I suppose it was mainly 4.3, getting used to logarithms, learning that logarithms are the opposites of exponential functions, right? And when I say opposites, I should really say inverses. They're the inverses of exponential functions. But now we're going to be looking at laws of logarithms, which is basically what this section is going to be. Is I'm going to give you some rules, and we're going to practice using the rules. It's going to be really straightforward, probably going to seem easier than the previous section. So let's get straight into it with these rules. Well, actually, no, let me say one thing before, just to remind you like what logarithms do, right? Let's say if we have some equation, so just a reminder, let's say reminder over here, what do logs do? Or why are they useful? If I have some equation like 2 to the x and then is equal to, I don't know, 5, something like this, where the exponent is buried up in the, or the variable is buried up in the exponent position, then what I do is I need to introduce a log on both sides with the matching base, so a base of 2 in this case, because the base of the exponential function here is 2. I introduce a log base 2 on both sides. Log base 2 of 5. So on the left-hand side, the log base 2 and the exponential function of base 2 cancel each other out. They cancel each other out and just the x pops out. This is because they're inverse functions of one another. And over here, I just get some number that, we don't know how to calculate this yet. We don't know how to calculate something with a weird base like 2. We know how to calculate it if it has a base of like 10 or e, right? There are buttons on the calculator for those two bases. But here, we don't have the tools yet to calculate this. But this is what logs do. They solve, or one of the things they do, right, is they are useful for solving equations where the exponent is buried up in the, sorry, I said it again. The variable is buried up in the exponent position. Okay. Okay, so now let's get into these properties. So property 1 says that if I have the log base A, so just some generic base A, of a product, A times B, so that's A times B, then that's the same as splitting the log into a sum. This is, what is this? What is the analogous version in for exponent rules? Because this should seem kind of familiar to an exponent rule, where if you multiply two things that have the same base, then you add the exponents. So the analogous version of this in the exponent form would be if I had like some exponent, some base A raised to some exponent capital A, and then times that same base A raised to exponent of B, then that tells me I do A raised to the capital A plus capital B. So that's like the analogous version in the exponent rule. In fact, that's how you can prove this log laws. You can convert these all to exponent form, which we looked at how to do that too, and then exponent rules. Oh, okay. So
Hey,
this,
quick question.
yes.
I think that the screen is out of focus because I can't see anything.
Oh, okay. Okay, 1 second. Let me see if I can, hang on. Actually, I think I know the fastest way to fix this. I'm just gonna unplug plug it back in. Did that fix it? Oh, that's probably what that chat is about too. Yeah, okay. Does it look better now?
Yes, thank you.
Yep, cool. Okay. Oh, let me turn the light back on. Oh, okay. Okay. So we have this log law. So it says if you have a product inside the log, then that can be split up and written as the sum of two logs. Product inside means sum outside. That's how I remember it. Product inside means sum outside. Okay, then we have a very similar rule for division. If there's a quotient inside, then that means subtraction outside. So that should seem, that hopefully makes sense there. Product inside means sum outside, then quotient inside means subtraction outside. And the analogous version here in exponent form would be if I've got two things of the same base, so some base lowercase a here is just the generic base here with these exponents capital A and capital B, then we know that the exponent rule tells us to subtract like that. So what's happening in blue, I'm writing like the analogous version of the exponent rule. And notice the exponent rule says difference inside means quotient outside. That's one way to interpret this. Subtraction up in the exponent position means split it apart and divide outside like this, a quotient outside. And the log rule is reversed, right? Because they're inverses of each other. Logs and exponentials are inverses. So the log rule says a quotient inside means a difference outside. Difference meaning subtraction, right? Okay, and the last law here that we will make use of is if you have, that's a capital C, log base A of some number raised to an exponent, then you can plop that exponent outside, oops, log base A, like this. You can drop that exponent outside the log and multiply it to the outside of the log. So is there an analogous version of this in the exponent laws? Maybe exponent raised to exponent? Does that make sense here? A raised, not really. Anyways, yeah, okay. So I won't write an analogous version in the exponent laws for this one. I don't want us to have to think too hard about that. Okay, so here are our three new log laws here. And there's going to be more. There's going to be one more really important law coming later in this section, but for now, let's just practice using these. Let's just practice using these three laws. By the way, they're all in a nice little box on page 390 in the textbook. So if you have the ebook open, you can go to that page and just have it open as a reference. So like I said, this section is going to be pretty straightforward, writing down laws and then practicing using them. So evaluate each expression. In the next section, we'll actually get back into some solving. We're going to do solving log equations and solving exponential equations, and we'll be able to get back into some application type problems. So let's say we have log base 4 of 2 plus log base 4 of 32. Okay, so in its current form, if we were to try to, actually, before I start thinking about this, let me write down the other problems so they can all be up here at the top of my page. Log base 2 of 80 minus log base 2 of 5, and then C is negative 1/3 of log of 8. Okay, now I'm going to start thinking about part A here. So if I try to evaluate each of these individually, and when I say individually, I mean this log and this log, then I need to ask the question, 4 raised to what power is equal to 2? And that, you know, we could get some kind of fractional answer for that, but maybe there's a better way. And over here, 4 raised to what power is 32? So neither of these is going to be a whole number. This would be fractional, and this would be fractional as well. So we don't want to deal with that. So maybe we can combine them, and then the log will be easier to evaluate. So how do we combine them? Well, we're going to use log law 1, which says that if you have a sum, right, just like we do here, a sum of 2 logs with the same base, then you can stuff them together and say that it's the same as, so log base 4 of 2 plus log base 4 of 32. You can stuff them together and say that it's the same as log, same base, therefore, of 2 times 32. I'm using this law in reverse, right? Going from sum outside to product inside. And then, of course, this is log base 4 of 64. And now this is going to evaluate to a nice whole number, because what is 4, or rather, what number do you have to raise 4 to get 64? Remember, that's the question this log is asking. What number do you have to raise 4 to get 64? And once we think about that for a bit, we'll remember that 4 cubed is 64, so this answer is 3. I'll say because 4 cubed is equal to 64. That's why log base 4 of 64 is equal to 3. Okay. So any questions about that one so far? Seeing the use of the law here. Okay. Let's look at part B, which is clearly going to be using the other rule, right? The other rule, meaning law 2 here, that says if we have a difference of 2 logs, then we can stuff it together. If it's a difference outside, we can stuff it together and make it a quotient inside. So we have to remember that the operation changes. So we're not going to do like 80 minus 5 inside, right? It's going to be 80 divided by 5. So first it's going to be a difference of 2 logs. And then that's going to be equal to a quotient inside the 2 logs. And the order matters here, right? It's this divided by this. When you stuff it inside, it's 80 over 5. And think about what is 80 divided by 5. Think about that for a second. We get 16. And now this is going to evaluate very nicely again. So notice these 2 pieces back here that made up this difference, they don't evaluate nicely, because it's asking, what do you raise 2 to get to 80? Well, 80 is not a power of 2, so it's some, not whole number. And same thing for the 5. What do you raise 2 to get to 5? Well, that's definitely not a whole number. But when we stuff them together, we get this relationship, and this does end up being a whole number. It's much easier to evaluate. And why is it 4? Because 2 raised to the 4th is 16. Okay, so that's the second law. Now let's practice the third law, which part C is asking us to do here. So actually, we could evaluate part C in the calculator, because remember that this is a special kind of log. This is a log with base 10. This is a log with base 10. When the base is not explicitly written right there, then it's understood to be a base 10. So I could do in the calculator, I could hit -1/3, so that's -1/3, and then times log of 8. And I could just evaluate it just like that, and I get my answer, and I could round. See if you guys can see that. There we go. And I could round appropriately, and that would be it. But let's go ahead and practice using the law, the third law here, which says that if you've got something multiplied on the outside of the log, like we have here, that -1/3 on the outside, then you can bring it in and turn it into an exponent inside. And let's just do that just to practice using this law. So we would say log of 8 raised to that thing that was multiplied on the outside. So raised to -1/3. And you might say, why the heck would I ever want to do that? That's just so much worse. It's literally a negative fraction up in the exponent position. But remember that all this means, well, there's no, do this off on the side. Do some side work, maybe over here. 8 to the -1/3 is the same as, first of all, what does the negative do? Well, the negative makes it flip to the bottom, like this. 1/8 to the 1/3. And what does a 1/3 exponent mean? Well, that's a cube root. So that's what that means. And then what is the cube root of 8? What times itself 3 times equals 8? So all of this that I'm doing over here in blue has nothing to do with logs. It's everything to do with that negative fractional exponent up in the top. Okay, so the negative flips the whole thing to the bottom. And then the fractional exponent turns into a root, if you recall that all the way from the beginning of the semester. And then we just have to know cube root of 8 is 2. So that means that this turns into log of 1/2, because this terrible 8 to the -1/3 just actually cleaned up very nicely into a log of 1/2. And now, since this is a nice log that has a base that can be plugged into the calculator, I can just say log of 1/2, and it's going to give me the same answer I got a second ago, right? Because remember, we did this, I'll just say 30. I'll just do that. I'll just round to the 100th place. We only remember that we didn't need this law to be able to evaluate this expression. We just used the law to push this into the exponent position just for practice, right? Just for practice. Okay. Let's use the laws in the other direction. So instead of taking things that are expanded and compacting them, let's go the reverse direction. Let's take things that are compacted and expand them as far as they can be expanded. Okay. So the idea is that in the end, we will have only one thing inside each log expression. Like the input for each log should only be one number. No exponent, no root, no product, just one thing. Okay, so let's look at this first one. It's a log base 2 of 6 times x, right? It's 6x, so that means 6 times x. That's going to be a use of this log law 1, which says that I can expand this into a sum. So take the product inside and expand it into a sum. So log base 2 of 6 plus log base 2 of x. Just splitting that product into a sum, giving it each its own log, and keeping the base the same, right? The base is 2, should stay the same. Okay. And that's it. So clearly this right-hand term cannot be evaluated because it's got an x, right? We don't know what x is. This could be evaluated to be an actual number, but we still don't have the tools to know what to do with that base of 2, right? We only have a button on our calculator for a base 10 log, which is the log button, and a base E log, which is the ln button. So we really can't get any further yet. So this is the best we can do for this problem. All right, let's look at part B now. Now part B is a lot more going on. There is a product of x cubed and y to the 6th. So actually using the same log law, I can split that product into a sum of 2 logs, like that. Okay, so that's just like the first one so far, right? Just splitting that product between x and y up into a sum, each in their own log. But we can also now use law 3 to take the exponent on each of these things and stuff it outside of the log. So what I mean by that is we'll say this here, the 3 in the exponent position on the x gets stuffed outside like this. So we'll say 3 times log base 5 of x. And then similarly, this one will be 6 log base 5 of y. And that's as far as we can go with this one. So you see how there is only one thing left in the input. Whenever you're asked to expand a log expression like this, your last answer should only have one thing in the input position for the log. No exponent, nothing else, just like in this case, just an x, and then in this case, just a y. Okay, I'm gonna leave a little space because we're getting a little cramped up here. I want to space this one out. So ln, now this one has a lot going on. We're going to need all of the rules for this. We're going to need law 1 because we have a product of a and b. We're going to need law 2 because there's a difference, a quotient, and we're going to need law 3 because of this root, because I know that the root can be written as an exponent, so that means that exponent's going to have to come outside. So now we get into a problem of like, which one do I do first? Which one do I do first? So we're going to want to be careful about which ones we do first. In this case, you actually don't need to be too careful. You could probably do it a couple different ways. But what we're going to want to do first is get rid of the quotient. That's going to probably be the best thing to do. So we're going to want to get rid of the quotient, or rather expand the quotient. So what I mean by that is the first thing I'm going to go for is this little division that's inside, the quotient inside, and turn that into a difference. So I'll say ln of that numerator, AB, and then minus ln of that denominator. So that's a use of law 2 there, using law 2. Okay, now I'm going to say, oh, look, now I have a product. I can split this into a sum. So this one, this first term here is going to turn into ln of A plus ln of B. Okay, so that's this term. And then minus ln of cube root of C. But remember I said that inside of each log, there should only be one thing going on. So these are done. This one's done. This one's done. This one is not, because it still has a cube root in there. And I know that I can write a cube root as a fractional exponent. In fact, 1 over 3 in the exponent position. So if I do that, ln of a plus ln, just copying these down, and then minus ln of c raised to the 1/3. That's fine. It's just exponent rules there, or rather root rules, cube root rule. And now I can apply that third law that says I take that exponent and plop it on the outside of the log. And now I'm done. Okay, let's do another example. Just more practice with these laws. Are there any questions so far, or do you want me to go back over any of these? Okay. Example 3. This one's going to be similar to example 1 in that we're going to be compacting them. In example 1, we actually wanted to evaluate them, so we actually got like a number answer at the end. In these, we're going to be using the same laws to compact these expressions, but we're not going to evaluate them because they're going to have variables in them. So the instructions say to combine each expression into a single logarithm. So the first one, part A, is 3 times log of x plus 1/2 log of x plus 1. And part B is 3 natural log of s plus 1/2 natural log of t minus 4 natural log of t squared plus 1. Okay. Part A. First thing I'm going to do is get these things that are multiplied on the outside of each of these logs, and I'm going to stuff them in as exponents. Okay, 3. Let me just rewrite the expression. There we go. So I'm going to say equals, and then log of x cubed, using that third law there, pushing that 3 in as an exponent. And now here I need to be careful because I need to make sure I'm raising the entire input here to the 1/2. When I bring the 1/2 in, I'm going to have my parentheses for the input of my log, and then I'm also going to need to wrap x plus 1 in parentheses and raise it to the 1/2. Just making sure that the whole thing inside is raised to the 1/2. That wasn't an issue with the first one because it's just a single term, right? Just put the 3 on it, that's all you need, right? Okay, so am I done? No, I'm not done yet, right? Because I need to combine them into a single logarithm. This is still 2 logarithms written as a sum, but I know how to deal with the sum. I can compact it into a product. So I take log of the product of these 2 inputs. So I'm going to multiply x cubed times this input, so literally just write them next to each other like that. There we go. And then from here, is there much more you can do? Not really, right? I know the 1/2 can be written as a square root, so if I prefer that notation, I could say x cubed and then square root of x plus 1. That allows me to drop those extra parentheses, I suppose, if you prefer that, but other than that, there's nothing else to be done here. Okay. Let's try part B. Oh, by the way, why am I allowed to do all these laws? It's because the logs here have the same base. in fact, they're both base 10, right? When the number is not written, we know it's base 10. So they're both base 10. So I'm allowed to stuff them together and do whatever I want with them like this, right? All these laws, the condition is that the base has to be the same, right? Okay. So this one has a lot more going on. S plus 1. I'm rewriting it first. Okay. Let me bring in all these numbers that are on the outside in as exponents first. That's using law 3. So typically when you're doing something like this, law 3, if it's necessary, if you need it, is a good place to start when you're compacting things. Though notice when we went the other way, law 3 was the last thing that we did. When we were expanding things, law 3 was the last one that we dealt with. Okay, so first I'll say ln of s raised to the third power, that's the first term, plus ln of t raised to the 1/2 power, just bringing that 1/2 in, and then here minus ln of, and again, going to need to make sure I double up on the parentheses here, so I say t squared plus 1 raised to the 4th power, and then close the input of my natural log function there. So I don't put the 4 out here, right? Putting the 4 out here would mean the log was being raised to the 4th power. That's not what's happening, right? The log is not being raised to the 4th power. Its input is being raised to the 4th power. Okay, and this is an S. All right, so now I can start sticking things together. I'll go ahead and say this sum turns into a product, so that can be written as ln of s cubed times t to the 1/2, just like that, and then copy this second term down, this last term to the 4th. Okay, so that's just using law 1 there, writing the sum outside as a product inside. You don't need the little multiplication dot, I just put it there just for clarity, but you could just stuff those numbers together, s cubed, and then stick t to the 1/2 right next to it. Okay, and then now I've got a difference of 2 logs, so I can write that as a quotient. And yes, there's a lot going on here and a lot going on here, but all I need to know is that if I have a difference of 2 logs and they have the same base, in particular the base is e here for these 2 logs, then I can just write this as a quotient with this being the numerator and this thing, the other input, being the denominator. So t squared plus 1 raised to the 4th. Cool. So one thing to note is that there is not a rule that says something like there is not a rule that says this. It's important to not get mixed up on that. Okay, this is not true. Not true. Right. Remember that the rule says so let me compare that to the actual rule. The rule says a product inside turns into a sum outside, not a sum inside, right? You can't do anything with a sum inside. So I think the best way for me to remember it is to think of them as, in fact, I'm going to rewrite them. I'm going to rewrite these 3 laws just in words. Product inside a log equals sum of 2 logs. Right, that's the first law. Product inside equals sum of 2 distinct logs. And then quotient inside, so that means like a division, equals not a sum, but a difference, which means a subtraction problem, right? A difference of 2 logs. So that's law 1 and law 2. I'll number them for you. There you go. And I guess I can write the third law as, so here's the third law. How should I say, exponent inside a log. Wow, okay. Just the n there. Inside a log is equal to a product on the log. I think that's maybe the best way to say that one. So if there's an exponent inside the log, that letter C there, then that is equal to the product on the log. Like you stick the C outside on the log, on the outside of the log. Maybe I should say, maybe we should say on the outside of the log. Okay, where are we now? Okay, any questions or comments so far, or need to see any of the previous problems again, or anything like that? Okay. Okay. Give me 1 second. We're going to now talk about a change of base formula. So finally, we're going to get the thing that we need to be able to evaluate things that have a weird log base, like this problem I gave earlier as an example. This is still something we cannot evaluate, but we're going to now build up the property that lets us actually solve these. Okay, just give me 1 second. I gotta think. Okay, let's take let's take a generic, let's attempt to solve a generic, so with no numbers, exponential equation. Okay. So let's say b raised to the y is equal to x. And we want to solve for y, right? That's the whole point. The thing that's hard to solve for is the y, right? So we're going to try to solve for y. Okay. So let's take normally we would want to take a log b, right, to cancel out this b here, but let's take just a generic log on both sides, log base a, b to the y equals log base a of x. Okay, so we're taking log base a on both sides, so just some generic log of base a. Why would we do that? Well, now we can take this y, use law 3, and plop the y on the outside. That's fine. That's just a use of the law 3 happening there. So that's all I did there, is use law 3 to take the exponent and stuff it out on the outside there. And now I can say, I can divide this entire log over here, right? I can divide this entire thing, because this is attached by multiplication now. So I can divide under this log, so log base a of x over log base a of b. Just divide that whole thing over. It's no problem. This is just a number, so just divide it all the way over. And now I have it. I have y is equal to log base a of x over log base a of b. But that's still maybe not so great, because what is log base a? Well, also note that from this b to the y equals x, b raised to the y is equal to x, that can be rewritten as log of base b of x is equal to y. Remembering all the way back from the beginning of 4.3, we can rewrite any exponential equation in this form. That was like the first definition of the log that we saw. You can rewrite any exponential equation in a log form. It has the same base, so the base of the exponential is the base of the log, and then the y is explicitly solved for over here, and the x ends up being the input of the log. So what does that mean here? Well, if y is equal to this thing, then I can replace this y with this log expression. So log base b of x is equal to log base a of x over log base a of b. So you see where the b and the x went. The b goes down here and the x goes up here. And then where a, that base a, is whatever we want it to be. Okay. Now, this may not seem profound. Maybe you might be confused about what this is saying, but this is saying that if I take any log that you give me with any crazy base, then I can rewrite it as the difference of two logs with some base that you get to pick. And by the way, what base will you pick? Well, probably the kind of log that you can be able to plug into the calculator, right? Like let a be 10 so that you can just use this button for it. So this lets us solve things like log base 2 of 5, which previously we could not have solved, right? We could not have evaluated. We didn't even know how to do it with a calculator. But now this tells me that I can say that this is equal to log base a of x, where x is the input of the log. So by the way, what do I want a to be? I'll just let a be 10 so that this is a common log. So I'm going to let a equal 10 so that it is a common log, can be plugged into calculator. So I'm going to say log base 10, which means I don't need to write it, right? If it's not written and it's understood to be 10, of x, which is 5 in this case, over log base 10 of the base. See where the b goes in this formula. B goes to the bottom in the input there. And this can be evaluated in the calculator because this is nothing more than log of 5 divided by log of 2. And it's going to give me approximately 2.32. So now we know how to evaluate any log expression with any base. Okay, so let me officially write down this formula for you. I'll give it a name, kind of clean it up a little bit, and then we'll practice using it. Okay, so it's called the change of base formula. It says log base b of x is equal to log base a of x over log base a of b, which is exactly what I wrote down up there, so that's not much more helpful. But now I'm going to say what it lets us do. we can choose any value for a. So let a equal 10. Then the formula is, so if a is 10, then we don't have to write it in the base because it's understood if you don't write it, it's a 10. So we have log base b of x is equal to log base 10 of x over log base 10 of b. This lets us evaluate any log with any base. This lets us evaluate any logarithm with any base, which is something we couldn't do before. So this is a big formula. Oh, did I? There we go. Okay. What example are we on for? Did I skip one? Oh, yeah. Okay, let's do example 4 now, which is example 5 in the textbook. I'll rewrite that formula as we use it. So example 5 says use the change of base formula. Oh, by the way, we could have also just so we have 2 log buttons on our calculator. The log base 10, which is just the LOG button, and the natural log. We could have used the natural log here. If you prefer that one, you can do that. In your formula, as you write all of this, you would say let A be the letter E, the number E. Then the formula would be log base B of x equals ln of x over ln of b. You can do that as well because that's a button on the calculator that you can make use of, but it's going to be one or the other, either the common log or the natural log. Okay. Oh, and they tell us in this example to evaluate each rounded to 5 decimal places. Okay. Log base 8 of 5. Part B says log base 9 of 20. Okay, so remember what these are asking. They're saying, like part A, well, let me give you a second to write it down before I keep going. Okay, part A, if we were to ask it in the sort of naive way, it's saying 8 raised to what number is equal to 5? And that surely does not have a whole number answer. It's going to be less than 1 because 8 raised to the first power is 8, right? So it's something less than 1. How can we figure it out? Well, whoops, I'm going to mix these up. 8 and 5 is inside. Well, I can write this using my change of base formula as log of 5 divided by log of 8, just like that. Just pop that into the calculator. I'm going to say approximately because we're going to round. So log of 5, just got to make sure I'm dividing in the right order. Log of 8. So the the input of the original log goes up top and the base goes in the bottom. Okay, so I'm getting 0.77397, but I'll round that 7 up to an 8. 77398. Okay, and now the second one, part B, log base 9 of 20 can write that as a log base 10 of 20, that common log, over a log, the common log of 9. And 9 raised to what is 20? Again, that's impossible to answer as a whole number. But we do know it's going to be between 1 and 2 because 9 raised to the first power is 9. 9 raised to the second power is 81. So 20 is closer to 9 than 81. So I'm expecting like 1.2, maybe 1.1, something like that. Okay, let's see what it actually is according to the calculator. Let's get an approximate answer here. Oh, I was off by, it's 1.3. Okay, 1.364, I lost count. 3634, 36341, but I round that up to a 2. Okay, 36342. So there we go. Now we have all of the tools that are going to allow us to solve all sorts of log equations, which is what the next section will be. So I'm going to have some problems from this section. Have I been sending you? I think I did in the chat, hopefully. Yes. Okay. So I'll be updating that list of problems to mark for review. Keep up with the WebAssign too, but the problems I'm sending you to mark for review are what you need to look at as very specific practice for the final exam. So we're done with 4.4, so I'm going to update it in just a moment after our meeting and send you some problems to update that list for 4.4. And then next time we'll start 4.5. So are there any questions about any of this stuff before we conclude 4.4? Okay, you guys are good to go. I will see you on Wednesday.